All right, let's go.
Number 7. Closed Timelike curves. Why Einstein's own equations are the problem physicists have been trying to solve. General relativity does not forbid time travel. This is the uncomfortable starting point for everything on this list. Einstein's field equations describe how mass and energy curve spacetime. Solve those equations for certain exotic configurations, rotating black holes, cosmic strings, traversable wormholes with their mouths and relative motion, and you get something called a closed timelike curve, a path through spacetime that loops back on itself. Follow it forward in your own proper time, obeying every local law of physics at every step, and you eventually arrive back at your own past. This is not a hypothetical loophole someone found by breaking the rules. It falls directly out of solving Einstein's own equations correctly. Kurt Gödel found a rotating universe containing closed timelike curves in 1949 while working alongside Einstein at Princeton. Kip Thorne and his students showed in 1988 that a traversable wormhole with one mouth accelerated to near light speed and returned becomes a time machine. Physicist J. Richard Gott showed in 1991 that two infinite cosmic strings passing each other at sufficient speed produce closed timelike curves. Every attempt to mathematically prove time travel is impossible has to start from this uncomfortable fact. The theory that describes gravity with more precision than any other theory in physics, confirmed by gravitational wave detections, by the bending of starlight, by GPS satellites correcting for it every second, also permits time loops. If physicists want to prove time travel cannot happen, they cannot do it by pointing at general relativity. General relativity is the problem. The proof has to come from somewhere else. Number 6. The Chronology protection conjecture. Hawking's attempt to save causality by force. In 1992, Stephen Hawking published a paper with the deliberately blunt title, Chronology protection conjecture. His claim, stated in his own words, the laws of physics do not allow the appearance of closed timelike curves. His reasoning was not philosophical, it was quantum mechanical. As any system, a wormhole or region of curved spacetime, approaches the point where a closed timelike curve is about to form, quantum field theory predicts something catastrophic happens first. Virtual particle pairs are constantly appearing and disappearing everywhere in the vacuum, a standard feature of quantum field theory. Near a forming closed timelike curve, calculations show these vacuum fluctuations begin looping around the nearly closed path repeatedly before the loop even fully closes. Each loop adds more energy. The renormalized stress-energy tensor, the mathematical quantity describing the energy density of the quantum vacuum at that point, diverges, shoots toward infinity. An infinite energy density at exactly the point where the time loop would close destroys the very space-time structure needed to create it. The wormhole throat collapses. The region becomes singular. Nature, in Hawking's framing, closes the door on itself a fraction of an instant before the loop can complete. Hawking supported his own conjecture with a joke that was also a serious empirical observation. He noted that we have not been invaded by hordes of tourists from the future. If time travel to the past were ever going to become possible at any point in the future history of the universe, the argument goes, we should expect to have already met visitors from that future by now. We have not. Hawking treated the total absence of any confirmed time traveler as informal but real evidence supporting his conjecture. The chronology protection conjecture has never been proven. Hawking himself acknowledged this. It remains 34 years later exactly what its name says, a conjecture. Number 5. Vacuum polarization and the defense in depth argument. Multiple independent mechanisms all fighting the same battle. Physicist Matt Visser, working through the early 1990s, took Hawking's conjecture and asked a more specific question. Even if quantum vacuum divergence is real, is it the only thing preventing time machines? Or is nature attacking the problem from multiple directions simultaneously? Visser's analysis, published across several papers, identified what he called a defense-in-depth strategy. Not one mechanism, several, operating in different regimes, each capable of destroying a would-be time machine independently. the Casimir effect, a genuinely measured phenomenon where two closely spaced conducting plates experience a real confirmed force due to quantum vacuum fluctuations between them, contributes one layer. In wormhole geometries, similar effects can produce runaway energy densities as a closed timelike curve tries to form. Wormhole disruption effects contribute a second layer. Even setting aside vacuum divergence, the sheer act of trying to convert a normal wormhole into a time machine, accelerating one mouth to create the time offset, requires enormous energy inputs that themselves destabilize the wormhole's throat through ordinary gravitational back reaction, independent of any quantum vacuum argument. Gravitational back reaction contributes a third layer. As particles and fields loop around a nearly formed closed timelike curve, their own gravitational influence feeds back into the geometry that is trying to produce the loop in the first place, distorting it before closure. Visser's conclusion was cautious rather than triumphant. He described the situation as nature appearing to fight the formation of time machines using every tool available, at every scale, simultaneously. But he was explicit that no single one of these mechanisms had been rigorously proven sufficient on its own to guarantee that all possible time machine configurations fail. It reads like strong circumstantial evidence for chronology protection. It is not, mathematically, a proof. Number 4. Quantum field instability at the Cauchy horizon. The most recent direct attack, 2025. Every closed timelike curve solution in general relativity comes with a boundary called a Cauchy horizon, the surface marking the edge of the region where the normal deterministic evolution of physics from initial conditions breaks down, because beyond it, the past can be revisited. In 2025, a study examining the Kerr-Newman spacetime, the exact solution describing a rotating electrically charged black hole, which contains closed timelike curves deep inside it near the singularity, modeled the behavior of quantum scalar fields, specifically at the inner horizon where those curves would exist. The result reinforced Hawking's original mechanism with more mathematical precision than had been previously available for this exact spacetime. The quantum fields examined showed exponential instabilities at the inner horizon. Small perturbations to the fields do not stay small. They amplify exponentially as they approach the region where closed timelike curves would form. This amplification is precisely the kind of process that, in Hawking's original argument, was expected to drive the local energy density toward divergence and destroy the horizon's structure before any observer could actually use it to travel backward in time. This 2025 result is important because it's not a generic argument applied loosely to an idealized wormhole. It's a specific calculation applied to the Kerr-Newman spacetime, the type of rotating charged black hole that is at least plausible as something that could exist in nature, unlike some of the more artificial exact solutions used in earlier chronology protection papers. Finding the same exponential instability mechanism operating there strengthens the overall case that whenever general relativity tries to hand you a genuine time machine, quantum field theory arrives to break it. It is still not a full proof. It is one more specific spacetime out of infinitely many possible spacetimes where the mechanism has been checked and found to hold. Number 3. The Second Law of Thermodynamics. An older, simpler, and less complete argument. Before quantum field theory entered the picture, physicists had a much older tool for arguing against time travel to the past: entropy. The second law of thermodynamics states that in a closed system, entropy, a measure of disorder, never decreases. This is why eggs scramble and do not unscramble, why heat flows from hot objects to cold ones and not the reverse, why you age forward and not backward. The astronomer Arthur Eddington called this the arrow of time and argued in the early 20th century that traveling into the past means traveling from a higher entropy state to a lower one, a direct violation of the second law. This argument has a well-known weakness, one that physicists have pointed out for decades. It says nothing at all about traveling into the future. Moving forward through time via relativistic time dilation, genuinely confirmed, genuinely measured, already used in GPS satellite corrections every day, does not violate entropy in any way, because you are still moving in the direction entropy already increases. The thermodynamic argument only bites on backward time travel specifically, and even there, physicists, including Eddington's own successors, have called the argument incomplete rather than a rigorous proof. The argument also runs into a serious mathematical complication once quantum mechanics is brought into closed timelike curve models directly. A study published in Classical and Quantum Gravity in December 2024 by physicist Lorenzo Gavesino, building on ideas from Carlo Rovelli, examined what actually happens to entropy and to the thermodynamic arrow of time for a hypothetical system traveling around a closed timelike curve. The result complicates the simple picture rather than confirming it. Gavesino's analysis found that on a closed timelike curve, quantum fluctuations can locally erase entropy in a way fundamentally different from ordinary experience, with energy levels inside a traveling system forced into a spontaneously discretized structure, finely tuned so that after a complete round trip around the loop, the system returns exactly to its initial state. Entropy that increased on the way out is undone on the way back, not through any violation of physics, but through the specific geometric constraint the closed loop itself imposes on what states are even allowed to exist. The thermodynamic argument against time travel, once treated with full quantum rigor, turns out to be far more subtle than Eddington's original 19th century intuition suggested. It is not a clean proof of impossibility. In Gavesino's framework, it becomes, instead, a description of exactly how a self-consistent time loop would have to behave if it existed at all. Number 2. Deutsch's quantum consistency model, the proof that accidentally proves the opposite. In 1991, Oxford physicist David Deutsch took a completely different approach. Instead of trying to prove closed timelike curves are destroyed before they can form, he asked what would happen to quantum information if you assumed they already existed and worked perfectly. His model, now known as the DCTC model, divides any system interacting with a closed timelike curve into two parts, a chronology-respecting part that experiences time normally, and a part that travels the loop. Deutsch imposed a single mathematical requirement, called the self-consistency condition. Whatever quantum state exits the closed timelike curve and rejoins normal time must be identical to the state that originally entered it. Not approximately identical, mathematically identical, described by a density matrix that maps exactly onto itself after the loop. This produces something remarkable when applied directly to the grandfather paradox. In Deutsch's framework, the paradox does not get blocked or destroyed. It gets resolved through quantum superposition. The traveler exists, upon return, in a mixed quantum state, a probabilistic combination of having killed the grandfather and having not killed him, correlated in exactly the way needed to satisfy the fixed point equation with no contradiction. A 2024 examination of the model, published as part of ongoing Quantum Foundations research, confirmed the mathematics hold together internally in a mixed state with roughly equal probabilities for each outcome, consistent with Deutsch's original 1991 derivation. This was intended, in part, as a demonstration that quantum mechanics could resolve the paradoxes classical physics could not. It was actually demonstrated, and what has troubled physicists ever since, that Deutsch's own mathematics does not forbid closed timelike curves from existing. It shows how to make them logically consistent if they do exist. Seth Lloyd and colleagues at MIT went further in 2011, publishing both a theoretical alternative, the PCTC or post-selected model, and an actual laboratory experiment using quantum teleportation to simulate the consistency behavior Deutsch predicted without needing a real time loop. Deutsch set out to show quantum mechanics resolves the paradoxes of time travel. He ended up demonstrating that if a closed timelike curve exists, quantum mechanics has no fundamental objection to it existing. This is the opposite of a proof of impossibility. It is one of the strongest pieces of theoretical work suggesting that if chronology protection ever fails, if a single closed timelike curve ever slips past Hawking's vacuum divergence and Visser's defense in depth, nothing in quantum theory itself would stop it from operating consistently. Number 1. What counts as a proof, and why nobody has one? Every attempt on this list shares the same final status: strong, suggestive, mutually reinforcing across multiple independent mathematical approaches, and as a matter of formal logic, incomplete. A true mathematical proof of impossibility would need to show for every possible spacetime geometry permitted by the equations of general relativity, an infinite space of solutions, that no configuration can produce a stable, traversable, closed time-like curve. What physicists actually have is a collection of specific case studies: Hawking's original semi-classical argument, Weiser's defense in depth across wormhole geometry specifically, the 2025 Kerr-Newman inner horizon calculation. Each one checks a particular spacetime or a particular class of spacetimes and finds the same qualitative pattern: vacuum energy divergence, exponential quantum instability, gravitational back reaction, killing the time loop before it can be used. The authors of the most detailed technical review of this entire field, published as ongoing lecture notes on faster-than-light and time travel physics, state the limitation directly. The chronology protection conjecture is plausible. We are nowhere near proving it, in part because we do not yet have the right tools to do so. A full theory of quantum gravity unifying general relativity with quantum mechanics in a way that currently does not exist would most likely be required to settle the question definitively. Until then, physicists are restricted to semi-classical gravity, quantum matter fields evolving on a fixed, classical spacetime background, an approximation, not the full theory. There is also a documented counterexample working against a universal proof. Physicist Li Mingbao showed in a specific spacetime construction that a closed time-like curve region could, in principle, remain stable against the very vacuum fluctuations Hawking's conjecture depends on, directly implying that Hawking's chronology protection mechanism, while apparently effective in most studied cases, does not appear to be universal across every possible geometry. So the honest answer, after 34 years of physicists actively trying to close this door mathematically, is this: every specific attempt to build a time machine that anyone has modeled in detail turns out to destroy itself. The pattern is remarkably consistent across completely independent mathematical approaches: quantum field theory, thermodynamics, gravitational back reaction. But a pattern across known cases is not the same thing as a proof covering all possible cases. Nobody has closed the door completely. They have simply found, again and again, that every specific door anyone has tried to build swings shut before it can be used. 7 attempts. General relativity itself permitting the loops in the first place, leaving physicists no choice but to fight the theory's own output. Hawking's 1992 conjecture that quantum vacuum energy diverges to infinity the instant a time loop tries to close. Weiser's defense in depth, showing multiple independent mechanisms attacking the same problem from different directions. A 2025 calculation on rotating charged black holes, finding the same exponential instability in one of the most physically plausible spacetimes yet examined. The Second Law of Thermodynamics, an older, simpler argument that a December 2024 paper showed was more subtle and less conclusive than a century of physicists assumed. Deutsch's 1991 quantum consistency model, built to resolve the paradoxes that ended up proving quantum mechanics, raises no fundamental objection to closed time-like curves existing at all. And the final honest accounting, a field full of independently converging evidence and not one single completed mathematical proof. Nobody has proven time travel is impossible. What they have proven, over and over in every specific case anyone has managed to calculate, is that the universe seems to want it that way. Subscribe to Cosmichives. See you in the next one.